discussing similarity. So let us start. Let us start by asking ourselves a basic question. What exactly is matrices similarity? Two n-cross-n matrices A and B are called similar if there exists an invertible n-cross-n matrix C such that the following condition is satisfied. And what that condition is? That condition says that if A equals C multiplied by B multiplied by inverse of C, and when we multiply the three together, if we get A back, then the matrices A and B are similar. One important word to note in this definition is the word invertible. We've discussed invertible before, but we will be discussing this again in the next slide. Moving forward, this equation can also be represented in the form of AC equals CB. We've shifted the C inverse on the left hand side now. So this is another representation of the same expression. This basically means that you can actually multiply the invertible square matrix with A, and then you can again multiply the invertible square matrix with B, and when you multiply the two together, the values of the matrix that you get should be equal to each other. That's when we can say these two matrices are similar to each other. With this definition equation, it's quite clear that matrix similarity is nothing but equivalence relation. So basically, when I'm saying two matrices are similar, I'm also saying that those matrices are equal. Let us discuss invertible matrices now. An n-cross-n square matrix A is called invertible or non-singular or non-degenerate if there exists an n-cross-n matrix B such that AB equals BA equals IN. That is, when you multiply the two matrices commutatively, you actually get an identity matrix. If you recall our previous discussions on identity matrix, you know an identity matrix has a value of 1 on its main diagonals and the rest of the values are 0. So this was a diagonal matrix. Everything else is 0, but the elements on the diagonal equals 1. Okay. So what is an invertible matrix? When you multiply the two matrices together, A and B, commutatively, that is in the order of A multiplied by B or B multiplied by A, you actually land with an identity matrix. Okay, moving forward. Some important observations about invertible matrix. The process of finding a matrix inverse is known as matrix inversion. Not all the matrices are invertible. As discussed, for a matrix to be invertible, it must be able to be multiplied by its inverse. Now, I want us to note here the two terms inverse and invertible, both being adjectives, might sound same, but they are two different concepts, okay? So you should keep that in mind. 0 has no multiplicative inverse, given we do not have any number that when multiplied with a 0 can give us 1. For sure, we don't. Additionally, a matrix might not have an inverse if it's not a square matrix. This is also an important point that you should remember. For a matrix to have an inverse, it needs to be a square matrix. Let us take an example. At this point in time, I would like to encourage our viewers to actually compute the solution of this problem with their own hands using pen and paper, because if you use your own hands to actually make computation, things are well understood and better understood. Okay, me just talking, you just viewing the slides and listening to what I'm talking might not give you the confidence. So feel free to pause the video, calculate the values, compare the values with the slide values, and then figure out if things are right or wrong and so on. So the question says, find the values of matrix P when matrix A and B are similar. So we're already given a condition that matrix A and B are similar. And these are the matrix values. We are supposed to find the value of this matrix P, which is A, B, C, and D. So we remember from a previous discussion If two matrices are similar to a third matrix, then that means this condition needs to be satisfied, correct? PA should be equal to BP, right? So let us represent this in the next slide. PA equals BP. We've represented the matrix as A, B, C, D multiplied with 1, 2, 3, 4. Then we have P as 6 minus 1, 4 minus 1. And we have P as A, B, C, and D. We've already discussed matrix multiplication, so feel free to pause the video here and compute the matrix multiplication values and then compare the values, okay? So let's multiply. We have to multiply the first row with the first column, A multiplied by 1 plus 3 multiplied by B, space 2 multiplied by A plus 4 multiplied by B, and then C multiplied by 1 plus 3 multiplied by D. Then you have 2 multiplied by C plus 4 multiplied by D, and the same has to be done on the RHS right hand side. Okay, so we have PA equals BP. Let's plug in the values. A plus 3B, 2A plus 4B, C plus 3D, 2C plus 4D equals 6A minus C, 6B minus D, 4A minus C, 4B minus D. So they'll be equal only if the values on the individual locations are equal. What do I mean by values in the individual location? So this is my first row and first column, correct? So this entry right here, A plus 3B, basically is an entry of first row, A of 1 and 1. The entry of A of 1, 1 should be equal to the entry of A of 1, 1 on the RHS side of the equation. So A plus 3B should be equal to 6A minus C. 2A plus 4B should be equal to 6B minus D. C plus 3D should be equal to 4A minus C. 2C plus 4D should equals 4B minus D. Let us now equate these equations. Let us bring all the values of the values that we have on the RHS to the LHS. So this equation will become A plus 3B minus 6A plus C equals 0. We're basically equating it with 0 and bringing all the values in the RHS to the LHS side. So this equation becomes minus 5A plus 3B plus C equals 0, 2A minus 2B plus D equals 0, minus 4A plus 2C plus 3D equals 0, minus 4B plus 2C plus 5D equals 0. A close attention quickly at these equations should give you an idea that we have one variable missing in each of these equations. So for instance, this is A, B, C. We have a missing D here. So let's just write here 0D. We have A, B, D here, but C is missing. So we have plus 0 of C. We have A, but we have a B missing. So we can just write 0 of B plus 2C plus 3D. And we have A missing here. So we can write 0A. Now let us combine all the coefficients together and then represent them in the form of a matrix, and then do the same with the variables and then equate it with a zero matrix. I'm quite sure that this representation should not come as a surprise at this point in time, because we've already seen a zillion times how we can represent linear equations in the form of matrices. So this should be a very pretty straightforward representation for everyone. But just in case you're new to the channel and you're seeing the first video as this one and you're not sure how we landed this representation from here, just refer to my previous sessions and it'll be clear. So let's take in the coefficients. We have minus 5, 2, minus 4 and 0. We have 3, minus 2, 0 and a 2. Oh, I'm sorry, B, sorry, we're reading B. The second column is for B, this is for A, this is for B. So this one is 3, minus 2, 0 and minus 4. Then the third column will become 1. We don't have anything here, 0, 2 and 2. And then the last column, which is for D entries, will become 0, 1, 3 and 5 respectively. Let's put in another matrix for all the variables A, B, C and D. We've equated all of them with a zero matrix. So this becomes minus 5, 3, 1, 0, 2, minus 2, 0, 1, minus 4, 0, 2, 3, 0, minus 4, 2 and 5. Clearly this matrix is not in row reduced echelon form, and we will have to bring the matrix to row reduced echelon form to compute any further values. We've already discussed what a row reduced echelon form is, and also we've discussed row echelon forms in the previous sessions. I'll link the URL in the description box just in case the terminology is new. So we have to bring this matrix down to row reduced echelon form, and before we do that we first have to reduce the matrix to row echelon form. So let's just go ahead and do that. And again, feel free to pause the video and then calculate the row echelon form yourselves and then the row reduced echelon form yourselves, and then start the video again and compare the values. This strategy will definitely give you more confidence on how you operate matrix questions. Okay, so let us start. Cancel leading coefficients in row R2 by performing the following operations. So we take R2 plus, we multiply 2 by 5 times of R1 and then add it to R2 and then display it as the values in the second row. So the values that we have are 0, minus 4 by 5, 2 by 5 and 1. Now cancel the leading coefficients in row R3 by performing this operation, that is R3 minus 4 by 5 times of R1, and then plug in this value in R3 row. So the entries in R3 becomes 0, minus 12 by 5, 6 by 5 and 3. Now let us swap the rows. So we swap the row 2 with 4 and vice versa. So swap itself means vice versa. So we've just swapped them. Cancel leading coefficients in R3 by performing the following operation. So from row 3 values, we are subtracting 3/5 of R2, and the values that we are getting equals all zeros. Cancel leading coefficients in row R4 by performing the following computation: R4 minus 1 by 5 times of R2, and then the value in the fourth columns are all zeros. Multiply matrix row by constant R2, so we're multiplying the second row with a constant minus 1 by 4, and the entries we have equal 0, 1, minus 1 by 2, minus 5 by 4. Let us now cancel leading coefficients in row 1 by performing the following operations: R1 minus 3 times of R2. So we have minus 5, 0, 5 by 2 and 15 by 4. And then now let us multiply matrix row by minus of 1 by 5. So we have a 1 here, 0, minus 1 by 2, minus 3 by 4, 0, 1, minus 1 by 2 and minus 5 by 4 respectively. So matrix right here was in row echelon form, and then we actually brought the matrix in row reduced echelon form, by getting the diagonal entries as 1. Again, a detailed description and a difference between row echelon form, row reduced echelon form, how do we define the two, is covered in the previous sessions, so feel free to refer to those videos. This is the final value that we've got for the matrix in row reduced echelon form. Let us now represent this in the form of parametric equations. We've also discussed parametric equations in the previous sessions, so feel free to pause the video in case you're not sure what the concept is. Refer back to the video and then start again from there, okay? So we had 4 variables, A, B, C, and D, and now we have the following row reduced echelon form of the matrix. So this can be represented as, you're just taking out the negative signs here. So you're just basically multiplying the whole expression with a -1 and a -1, and so we don't have the negatives left anymore. So this becomes half of t plus 3 by 4 of s plus half of t plus 5 by 4 of s. You can use any variables here, okay? It's just t and s that I've used, but go ahead and use any variables, doesn't make any difference. And t and s here because we have 4 unknown variables here, right? So let's just take out all the values here. We have 0s for simpler representation, and we have here a 0t. So let's represent t and s in the form of individual matrices. So this becomes half, half, 1 and 0, and t is out, plus s, 3 by 4, 5 by 4, 0 and 1 respectively. Now we need to replace the values of t and s such that we get integer values after adding the matrices together. So no much math skill required at this point in time. You can simply use t as 2, because if you divide 2 by 2 you'll get a 1, and 2 by 2 will give you a 1 here as well. And you can use s as 4, because if you multiply it by 4, 4 and 4 cancels and you get an int value of 3. Similarly, the same applies to 5 by 4. If you multiply it by 4, you actually cancel out the 4s and you get a 5 here, right? And then when you will add the two together, matrix addition, you'll actually get integer values. So let's just go ahead and replace t with the 2 and s with the 4. So this is what we have, and then let's go ahead and add them. We'll get 4, 6, 2, 4. If you remember, we had to find the value of P, which was a 2 cross 2 matrix. So we need to shift the column representation of this matrix to a 2 cross 2 matrix, which can be done as unders. P equals 4, 6, 2, and 4 respectively. So this is the value of P for which the matrix A and B are similar. This is how you solve such questions. Some very important conclusions. We've already seen equivalence relation, that when two matrices are similar, they are basically equal to each other, and since they are equal, the three properties holds good. What are the three properties? Reflexivity. So A is similar to itself. Symmetricity. If A is similar to B, then that means B is also similar to A. Transitivity. If A is similar to B and B is similar to C, then A is also similar to C. Just keep these properties in mind. Again, some very important conclusions. Say for instance, you're sitting for a data science interview and you're given two data set and you quickly ask that, have a quick look at this data set and tell if they are similar or not. How do you go about, answering such a question? So some important things that you can keep in mind is, as soon as you see some form of a data set, just take a subset of those information and put them in the form of matrix. Once you've put those information in the form of matrix, try computing their rank, trace, determinant, eigenvalues, and matrix powers. So for instance, if the ranks are similar, the traces are similar of the two data set that you've got, determinants are similar, eigenvalues are similar, matrix powers are similar, that means the data is actually of similar kind and they are similar data set. So this is how you answer questions associated with data refining, cleaning on an interview, exam, or anything like that. So matrices are going to be similar when they have same rank, trace, determinant, eigenvalues, matrix powers. We've discussed all these concepts in the previous session. What is a rank? What is a trace? What is a determinant? How do you find characteristic polynomial? And then compute the trace, and then how you find the eigenvalues, and then how do you compute the matrix powers. So if you are not sure in any of these concepts, I really encourage you to refer to our previous sessions, because they're really going to help you way down the line when you're implementing them in your data science problems. Mere understanding of functions in R, MATLAB, Python, whatever your programming languages wouldn't really help, but really understanding the core of the math, like I said before, many times will really help. So feel free to refer to those sessions just to understand these terminologies, because they're really important. Now let us do a conclusion of all the operations that can be performed on a matrix, which we've already discussed. Row echelon, inverse, eigenvalues, eigenvectors, determinants, trace, characteristic polynomial, minus, diagonalize, adjoint, rank, and transpose. So these are all the concepts that we've already discussed in the previous sessions. I'm guessing the viewers already know these terminologies really well. In case something is not clear, I really encourage you guys to actually understand these concepts properly through the previous sessions and figure out additional study materials, whatever is needed to get the concept in place, because they're really important. If you know the concept inside out, implementing them in any programming stack becomes really simple. So we've discussed all these terminologies and we've seen examples as well under these categories. But since these concepts are so important, and I would really want the users to actually have a 200% understanding of these topics, that I've decided to go about creating more videos with examples for each of these calculations. Like for instance, if you have an inverse based problem, how will it look, and then how you can go about making an inverse operation happen, and so on and so forth. So understanding the concept from the previous sessions and then taking the examples from the next set of series from the video lessons should help you understand all these operations a little more better. So that's pretty much it for this session. In case if you have any questions, feel free to get in touch through the website, or you can drop your comments in the comment section. Thank you so much.